Okay, this mini lecture is about solving and graphing inequalities and writing the answer in interval notation. So we're going to start with this first example here. This is called set notation. You see that this has the little braces, and that represents a set. And this is read the set of all x's such that x is greater than or equal to 3. And so this line means such that. And this is basically representing all the numbers that are greater than 3 or equal to 3. So 3 will actually be included into this set because of the equal to. Now, if we want to graph this solution as the directions say, then first we're going to fill out this number line. Many of the problems you don't necessarily have to start with 0, but let's just do it for this one so that we can refamiliarize ourselves with the number line. Okay? And this is going to keep going, and this direction will be -1 and -2. Okay, so at 3, we're looking for numbers that are greater than 3. So what numbers are greater than 3? Well, 4 is greater than 3. 5, which would be here, would be greater than 3. What about 3.5? That's greater than 3. 3.1, 3.001, so right up to 3 is greater than 3. And we also have this equal to mark, so this is saying or 3 itself. So all of these numbers going to the right are part of our solution set. Now, you may remember from high school or from another institution that in the past you may have put a open circle there on the graph to represent either less than or greater than, and you may have put a closed circle to represent less than or equal to, greater than or equal to. Here in college, we are going to do things a little bit differently. So instead of an open circle for less than or greater than, we're going to do parentheses. And instead of a closed circle, we're going to do brackets. And we're going to actually do that on the graph itself. So on this graph, we have an equal to. So right at 3, we're going to draw a line and make that a bracket going through 3, facing the shaded area. So this is sufficient to graph this set. Now, our interval notation is describing the shaded area from left to right. So if we start on the left side of the graph, what we're looking for is the first place that's shaded, and that happens to be 3. So 3 is where we start, and how far do we go? Well, this keeps going on and on and on forever. So in mathematical terms, that means infinity. So our starting place would be 3, and then we put a comma and we write where it ends. Well, because this doesn't end, we write infinity. And you should make a note that infinity or negative infinity is also going to get parentheses. So the only thing that's getting a bracket is when we have that line underneath. So this is going to be bracket 3, comma, infinity, close parentheses. All right, so notice that this was already set up as x greater than or equal to some number or x inequality some number. You didn't have to do any work for that. On example 2, it is not in this format. So we need to actually solve for x here. And you solve it very similarly to a linear equation. So for a linear equation, you're just solving for x by moving the x's together and the numbers on the other side. So we're going to do the same thing here. So we're going to subtract 6x from both sides. This is -2x minus 1 is greater than 9. And we're going to add 1. So I get -2x is greater than 10. And let me come over here and write that again because we're running out of room here. Okay, and then here's where things are different with an inequality. If I have a number in front of x and I want to divide both sides by this number, just like we do with the linear, if this number is negative, and in this case it is, then I would change the inequality sign. So you're going to flip this around. So instead of greater than, I'm going to have less than. Now this is not going to affect the answer itself. So this is still just going to be whatever you get. So 10 divided by -2 gives me -5. Okay. Now I'm not going to start at 0 here because that would make it really inefficient. So whatever we get here, this is what we're going to put in the middle of our graph. And I usually just go one down and one up, and keep in mind this is negative. So if I go one down negatives, that's going to be actually -6. And if I go one up, that's -4. Okay? All right, so we flip that over when we divide by a negative. I do want to say real quick that this number here that's on the right hand side, it does not matter the sign. If this was negative, it wouldn't matter. That does not determine whether you're going to flip this inequality over. It's only the sign of the number in front of the x. All right? So let's graph this solution. We have x less than -5. If you solve for x and you put the x on the left-hand side, you will always be told, this arrow will tell you which way to graph. So notice that this is pointing to the left, like it's shading to the left. Okay, and this arrow matches this arrow, so it's telling you which way to shade. If we logic this out, numbers that are less than -5 would be numbers that go to the left side of this. Okay, so we're going to shade first. Start at -5 and keep shading. Okay, and then let's go to our chart. This is just a less than. There's no equal to with it. So our less than had a parentheses. So right here at 5, we're going to do a parentheses through -5. Now always shade first so I know which way to, face that parentheses. All right. Interval notation. I talked about it being from left to right, and it is that way over here also, but I want to show you a little bit different way for this one. If we put the comma down first, I want you to think about which direction is this arrow pointing. This direction is left. Well, which direction do we shade? We shaded to the left. That direction is always going to be where the infinity sign is. So if this points left, you shade to the left, and infinity is on the left. So here we have infinity. And this makes sense because how far left does this go? Well, it keeps on going. The key on this one is that we are going in the negative direction. So our infinity will also be negative. And if we remember, infinity also gets a parentheses. Okay? And then on the other side is where it stops. So it is always going to be this number. So this number goes on the right-hand side, and it had a parentheses on the graph. So this is just different ways to represent the same thing. X is less than -5. This goes to the left side, and -infinity to -5. All of those mean the same thing and represent the same thing. Okay, so important, what do you need to remember when working with inequalities? When you divide by a negative, flip the inequality sign. Okay. My apologies for that technical glitch. Okay, moving on. We have absolute value equations. So notice that these have the equal sign in here and not less than or greater than sign. We're going to get to those, obviously, you see right here. So how do we tackle these absolute value equations? I want you to think about an absolute value and what it actually means. So if I had an absolute value of, let's say, 2, absolute value is the distance from 0 on a number line. So if I have a number line, and this is 0, and this is 1, and this is 2, how many units am I from 0? Well, I'm 1, 2 units. So this is why I get 2 for that answer. What is the absolute value of -2? Okay, so let's think about this. Again, this is the distance from 0 on a number line. So if this is -1, and if this is -2, then I'm also 1, 2 units from 0. So this answer is also 2. And so absolute value never gives you a negative result. The answer is always positive because distance is always positive. And the thing to remember with this is how many numbers, how many different variations can I have and get the same answer? And because the number line goes in the positive direction and the negative direction, you have two different things that you could plug in and put in the middle of this absolute value to get the same result. We have to take that into consideration when we're looking at absolute value equations and inequalities. So notice I can do a positive number inside and get 2, and I can do a negative number inside and also get that same 2. So that's what we're going to do here. We cannot work this with these absolute value bars still on it. So we're going to separate this into two different equations. And we're, by doing this, taking the absolute value bars off. So on this side, and this is really important that you pay attention to how I'm doing this, okay? On this side, you're going to write exactly what you see, except for you're going to take the absolute value bars off. So here I'm just going to have x plus 3 equals 2. Simple enough. On this side, I'm going to have x plus 3 equals -2. So I'm taking into consideration that I can get a positive or a negative inside, and it would give me that positive answer. I'd get the same thing, okay? So again, same thing on this side, change the sign on this side. So I'm changing it from on the right-hand side number. All right, now we're going to solve both of these. So -3 on both sides. Here I get -1. -3 on both sides. Here I get -5. Now the answer to this is not an interval. You just have two answers. It's just a solution, two solutions, -5 and -1. There's no parentheses because this is not an ordered pair. So you just list, similar to what you had for like quadratic equations or listing the zeros of a polynomial, okay? All right, that was the equations. What happens if we have inequalities? Well, the thought process is the same. We just have to kind of take this inequality sign into consideration. So we will have two different versions. On the right-hand side, this is going to be 2x plus 1 greater than or equal to 7. So notice it's exactly the same thing as the problem, just without the absolute value bars. On this hand side, we're going to have 2x plus 1, flip the inequality, flip. So instead of greater than, now I've got less than or equal to. And then we're going to change the sign of this. So we're doing a flip change here, -7. Setup for this is so important. Make sure you're putting the correct things on the correct side. Otherwise, you may still get the right answer, but you may not be able to interpret that very well because things are going to be kind of out of order. And you'll see what I mean in a minute. So let's solve both of these. So -1, I've got 2x greater than or equal to 6, divide by 2, and x is greater than or equal to 3. Here, -1, I've got 2x is less than or equal to -8, divided by 2, and x is less than or equal to -4. So what I meant was, if you put these in the reverse order, now you've got a negative on this side and a positive on this side, and even your number line is in the wrong order. So again, it's really important that you put what you see without the brackets on the right, and then flip change on the left, okay? Now, let's see what this means for the integral notation in the graph. So here I've got -4. Here I've got 3. Let's take it in pieces. So x is less than or equal to -4. So at -4, it's going to the left. This has an equal to, so at -4, I'm going to have a bracket. Again, that's the only time you have a bracket is if you have that little line underneath. Let me do this. There we go. All right, let's look on this side. 3, we've got x is greater than or equal to 3. So from 3, we're going greater than. That means it's pointing to the right, so we're going to shade to the right. And again, it has the little line underneath, so this is going to be a bracket facing the shaded area. Now, interval notation for this is quite interesting because we have 2 different intervals. So let's take it in pieces and then I'll talk about what we have to put in the middle here. So how would I write this interval? Well, if I'm going to the left, then this is going to be negative infinity up to -4. And one more time, just on that trick, if the arrow points left, you shade to the left and infinity is on the left and it's negative. Okay, let's look at this one. I've got an arrow that points right. I shade to the right and infinity is on the right. So on the left side here is the number. And I just realized I messed up right there because this should have been a bracket. So that should have been a bracket. Now, when you've got 2 different sets, 2 different intervals, but one answer, I need to be able to join these together in the same answer, in the same interval notation. And we use what's called the union symbol. Think of this kind of like, you know, 2 people getting married. It's a union of 2 people, right? So this is kind of the joining of 2 intervals together so that you can write it as one answer. Okay, so anytime that you skip over something, you skip over a part of the graph, whether that be a big segment or just one number, you're still going to put the union in here. Okay? All right, I have included a nifty little chart on the problem setup. So if it's set up like this, this is how, or if the problem is like this is how you would set it up. This is what your number line would look like, and this would be your solution set. Okay, so you can definitely use this as a reference as working your problems and helping you in your normal 101 class. All right, next page. I'm kind of moving on to a different type of information. So we're talking about domain and range now. We haven't really addressed this before now. We have kind of talked about, you know, graphs moving up and down. We've talked about circles that are in different locations. We've even talked about, and this is actually unit 9, I should say. We've even talked about, you know, transformations, making things wider and smaller, stretching, shrinking, reflecting, all of those things. Well, that changes the values of the graph and the x values and the y values. So now we're actually going to talk about defining that. What does it mean for domain? What does it mean to find the set of all x values? What does it mean to find the set of all y values? Okay, so this is what you need to remember. Your domain is the set of all x values that are defined in the function. They go from left to right on a graph. Your range is the set of all y values, and they go from bottom to top. And some students find it easier for me to say, this is the smallest x value to the largest x value, and the smallest y value to the largest y value. If that helps you, you may want to write that down. Okay. We have talked a lot about polynomial graphs, and most of these polynomial graphs do not have domain restrictions. That means that I can plug in any x number and we're good to go. So for example, like if I had x squared, there's no x's that I can plug in here that would make that undefined. I can plug in -1, I can plug in 1,000 if I wanted to, and I would be able to get an answer. Same thing with like a cubic, you know, if I had something like that, I could still plug in any number on the number line and get an answer. But there are a couple functions that we're going to talk about today that is not the case. These are called domain restricted functions. That means you cannot plug in every single number on a number line and get a value for y. So for these domain restricted functions, we're talking about two in particular. The first one is a radical function. So those are the ones that have the square root with it. The other one is rational, and those are the ones that look like fractions. So you need to remember that rational is the same thing as fraction. Okay? Now, let's talk about the radicals specifically. I want you to think about numbers that we cannot define in radical format. Or I should say, they are, what are our options for only real numbers? What makes an imaginary number? So remember, we've talked about radicals before, and that if we have a square root of a negative number, whatever that number is, I end up getting out an I. And this is what I'm saying is I can't graph that value on a graph. I want to be able to plug in numbers that I can't. So I need real solutions to this, not imaginary solutions. And I'm getting those imaginary from having negative numbers. So if I can't have negative numbers, that means I can only have positive numbers, because I could find the square root of any positive number, even if that number ends up being like 2 square root of 3. That's still a real number. I can put that in the calculator and find a decimal approximation. But what about 0? Could I find the square root of 0? Yes, that would be 0. So 0 works also. So really what I'm trying to find is any number that is 0 or higher. Because if it goes in the negative direction, we're no good, because we end up in imaginary territory. And that is what this is saying. That these numbers underneath must be greater than or equal to 0 in order for me to have a real number answer. Anything less than that is going to give me an imaginary number. Okay? So this is the setup you need to remember. And I'll say the numbers under the radical, but the name for that is radicand. So if the radicand, you're taking the radicand, just the number under the radical, and setting it greater than or equal to 0 and solving. You should note that the interval notation always includes a bracket. And why is this? It's because of that equal to right there. Okay, so let's look at this first example. We have f of x equals square root of x plus 1. Our radicand here is x plus 1. So if I'm following this format, I'm doing x plus 1 greater than or equal to 0 and solving. So this is minus 1, x is greater than or equal to negative 1. So now I can write this I can graph it and write it in interval notation. And when it's asking for domain, it wants it in interval notation. That's what it wants. It does not want you to write this. It wants the interval notation for this. So let's sketch a quick graph. If this is negative 1, I'm going to the right, and this is going to be a bracket. So interval notation, again, arrow points right, shade to the right, infinity's on the right, and the numbers on the left with a bracket. And that would be your domain. So your domain for this problem is all the numbers negative 1 to infinity. And let's see if that makes sense. If I plug in negative 1 in here, negative 1 plus 1 is 0. Square root of 0 is 0. What if I plug in 0? 0 plus 1 is 1. Square root of 1 is 1. Okay, and I could keep going. So any of these numbers would actually work in this and not give me an imaginary number. All right, so that's radical functions. You need to make sure you know the difference between the setup for radical and rationals. A lot of students mess this up. So keep in mind, this is going to be an interval greater than or equal to 0. This one is different, okay? All right, we've talked about rationals before. You've even graphed these with parent functions. And if you remember, the parent function of a rational looks something like this. And you know that for the x value, when the x value hits 0, it's undefined right through here. The graph never ever actually touches that. Okay, so this is because we cannot have a 0 in the denominator. And y'all know that that's just kind of like the normal rule for fractions. Okay, no 0 in the denominator. Think back to the slope. Remember when we were doing slope of lines and we had a 0 in the denominator? It was undefined. And that's a reason, because you cannot have a 0 in the denominator. Okay, so the setup for this is you set the denominator not equal to 0 and you solve. Our interval notation is going to include this union because we're skipping over some number. We're saying that there's some number there that's going to make that denominator 0. And again, going back, we also talked about this with rational equations when you had all those fractions in the problem and we had to figure out, is this a valid solution? Does this make this 0? Same thing here. Okay, so what I'm trying to find is, what is the x value that makes 2x minus 4 equals 0? And so what we're going to do is say 2x minus 4, we're saying, ooh, this cannot equal 0, because if it does, it's undefined. So let's see what that x value is. So that x value is 2. So let's see if that makes sense. 2 times 2 is 4, 4 minus 4 is 0. So 2 is not a valid answer, as in it's not in the domain of the function. It is not in the domain of the function. It's not, this number is not included in all the available x's. Okay, so if I was to graph this on a number line, this one's a little different. So here's 2. And what I'm saying is that 2 cannot be an answer. So even though I know we've done like parentheses and brackets before, here we are putting an open circle, but we're just doing that because there's a hole in the graph right here. And you can think about this is, you know, if we think about this, there's this place where the graph's not ever going to touch it. So it gets really close to this 2, but it doesn't actually touch it, but it can be every other number. Can be every other number. So how would we define this interval? This would go from negative infinity, all the way up to 2, really close to 2, but not including 2, so no bracket there. And then it's going to skip over 2, so that's union, because we're joining these two things together. It's going to start back up the other side of 2 and go on to infinity. This is the format for every one of the rational answers. So the only thing that's going to change in your answer for this domain are these two numbers. Okay, so it's always going to be negative infinity up to something, union something, infinity. Now, there are some more complicated problems where you may be skipping over 2 different numbers on your homework, but in general, this is the format. Okay? All right, let's move on. We're also going to talk about determining if a relation is a function. So we have a relation. A relation is just a relation between two sets is a collection of ordered pairs containing one object from each set. If the object X from the first set and the object Y is from the second set, then the objects are said to be related if the ordered pair XY is in the relation. A function is a special relationship where each input has a single output, which means that X values cannot be duplicated, and that's the key to this. So basically, it's a relationship between the numbers. It's like, hey, 8's going to relate to -9, 1's going to relate to 4, 1's going to relate to 2, 6 to 2, 3 to 2. Okay? And what we're trying to determine in this type of problem is if this relationship that we have drawn here is a function. And it's only a function if each input has a single output. That means this is only paired to one of these. Well, look at this one. This one is paired to this and this. So that's a problem. Okay, X values cannot be duplicated, therefore 8, -9, that's just one value paired with it. But if I was to write this ordered pair, I would have 1, 4, but then I would also have 1, 2. And because 1 is showing up twice, so I've got 2 numbers coming off of that 1, then this is not a function. Now, if this was a function, we may be able to come up with a domain and range. The domain and range would just be the set of all x values, and this first set would be your x's, and the set of all y values would be your range, and that would be your second set here. Okay? Let's look at this one. I've got 1 paired to 7, 8 paired to 4, 9 to 1, 7 to 3. So none of these x values are repeated, therefore this is a function. And if it is a function, we can list the domain. Now the domain is listed as a set, so we do the little braces, set notation. And we're going to have 1, 8, 9, and 7. And the range is going to be 1, 7, 4, and 3. And you're not going to repeat things in the same set. And we'll see what that looks like over here on this one. Okay? Now I do want to make a quick point. This did not happen in this one, but in this problem, we had 2 lines coming off the 1, and this was the part that was the issue. But notice that you actually had 3 numbers coming to 2. That does not matter. It does not matter how many numbers are pointing to this y value when it's talking about function. That will matter later when we talk about one-to-one functions, but when we're just talking about functions, this is irrelevant. So really what we're looking for is 2 numbers coming off any of the x values. All right? When it's listed as order pairs, all we need to do is just look at our x values and make sure they're not duplicated. So here we've got 3, 2, 9, and 6. None of those are duplicated, so is this a function? Yes, it is. Our domain is the set of all x's. So we've got 3, 2, 9, and 6. Make sure to use your little braces. And the range is the set of all y's, and this is what I was talking about. If it shows up more than once, so like here you have a 3 and a 3, you don't have to write 3 and 3 down here. You just write it one time, just one time. So I have 3, 4, and -5. Okay, so that's when we're given like a set or a relationship diagram. All right, looking at the next thing, we're talking about a vertical line test. So if we're given a graph, we can determine if it is a function by drawing a vertical line anywhere on the graph. If that vertical line hits the graph in more than one spot, the graph is not a function. So I want to just draw some examples so you see what I'm talking about. If I had a graph like this, and I drew some vertical lines on it, okay, notice that each one of these vertical lines is only hitting the graph one time. So no matter where I draw that vertical line, it's only hitting it one time, so this is a function. Yes, it's a function. Okay? What about like our standard parabola shape? Is that a function? Let's see. Now we need to keep in mind that this is going up and up and up and up and up, and that this is going up and up. And at the same time of going up, it's also going out slightly. So if I was to draw these lines, it still is only hitting it one time. Even though this looks like it gives the appearance of it hitting more than once, again, remember that this graph is going slightly to the left as it goes. So is this a function? Yes. What about a circle? Is that a function? So if I draw a vertical line, how many times does it hit the graph? It is hitting it 2 times, therefore it is not a function. Okay, and then let's do one more. What about our rational? Okay, so even though it looks really weird, this is actually a function. And this is because it's going to the left slightly, slightly, slightly every single time. So every time I draw it, I'm never going to hit it more than one time. Same thing here. Okay? All right, as you work through your worksheet, you need to remember that your domain from a graph, the domain from the graph is the leftmost x value to the rightmost x value. And your range from a graph is the bottommost x value, or the smallest y value, and topmost, or the biggest, largest, however you want to say it, y value. And you're going to have some examples of that, and I want you to think about going from left to right and going from bottom to top and describing the intervals for the domain and range for those graphs. Thank you for watching. If you have any questions, please let me know.